Well, here's an interesting theorem called Fubini's theorem. If f is continuous over a plane region R, and then if f is defined by a region where the x has number limits and y has a function of x as a lower limit and a function of x as the upper limit, and they are also continuous on the interval x equals a to x equals b, that's this interval, right? Then our double integral over the region R is the function f of x, y, dy dx, so order of integration is y first and x next. Y going from g1 of x to g2 of x, and x going from a to b. But if instead R is defined by this region, y varies between the number c and the number d, and x is between a function h1 of y and another function h2 of y, and those are continuous on this interval from c to d, then our double integral dA, remember I didn't specify an order for that one, but now I'm specifying, integrate with respect to x first, then with respect to y, our function f of x, y, x going from h1 of y to h2 of y, and y going from c to d. So, here's an example. Set up and then evaluate the integral that will give the volume of the solid bounded by, what's this? X squared plus y squared plus z squared equals r squared. And this is one, believe it or not, I can't get a picture of this one. And R can be defined as, the region R can be defined by x is a number between negative r and r. Think of what this is. This is a sphere of radius r. So I'm going to let x go from negative r to r, and y is from the bottom part of the semicircle negative. That's supposed to say negative square root of x, r squared minus x squared. The negative sign looks like it blended in with a radical sign, but that was an accident of software here. I can't zoom in any better than that. Is less than or equal to y is less than or equal to the upper semicircle. So there's our region R defined, right? So that this whole region, this whole thing is defining, this and this together define a circle of radius r. And our f of x, y, if you solve this equation for z, if you solve that equation for z, then z equals, let's see, z would be the square root of r squared minus x squared minus y squared. But I have to use a 2 on that, because if I just use positive that square root, then I'm only going to count the upper hemisphere, and I want the upper and the lower, so I multiply it by 2. That will give me the volume of this sphere if everything goes well. So here's our double integral. Y going from negative square root of r squared minus x squared to positive square root of r squared minus x squared. The 2, of course, is a constant. This is the function describing that hemisphere, and then x is going to go from negative r to r. So these limits of integration over here describe the circle, which is the region in the xy plane that this integral is all about. And so using a little further symmetry, you see if I go from 0 to r, that would say, well, that's just going to be half the circle, so then I just double it again, so that would make a 4 here. And then instead of going from negative square root of r squared minus x squared to square root of r squared minus x squared, I go from 0 to square root of r minus x squared, and that doubles it again, giving us 8 times the integral from 0 to r in the x limits, 0 to the square root of r squared minus x squared in the y limits of this awful thing here, square root of r squared minus x squared minus y squared. My program will do this symbolically, and the respected result follows. Okay, I'm just going to do that because, if I looked at this integration and wanted to integrate this with respect to y, I think you could see we might have some serious problems in there with the square root. We'd actually have to do that with the trig substitution, maybe y equals r sine of theta or something like that. But actually no, it would be worse than that. Something like y equals r squared minus x squared times sine of theta, and I really don't want to go down that road. So I'm going to use my software for that one. And if I do that, you can see the natural result I was expecting to get is 4/3 pi r cubed, because that's the volume of that sphere. Wow.
Wow. Wow.
And how?